Professor Nash, we want to congratulate you for being the Abel laureate in mathematics for 2015, a prize you share with Louis Nirenberg. What was your reaction when you first learned that you had won the Abel Prize?
Well, I didn't learn about it like a Nobel Prize, but I got a telephone call that was sort of later in the day, and it was confusing. I wasn't entirely surprised, but I had been thinking about the Abel Prize and how it was an interesting example of a newer category of prizes that are quite large and yet not entirely predictable. So you don't know how those would be sorted out. And so I was given sort of a pre-notification that was told on the telephone that it would be announced in the morning of the next day, and so to be prepared.
But it came unexpected?
It was unexpected, yes. I didn't even know what the time of the decision on Abel Prizes was. I'd been reading about them in newspapers and sort of not following closely.
When did you realize that you had an exceptional talent for mathematics? Were there persons that encouraged you to pursue mathematics in your formative years?
Well, my mother had been a school teacher, but more taught English and Latin. My father was an electrical engineer. He maybe was a school teacher also at an intermediate time before World War I. But for me, there came a time when in school I was just typically doing my addition, arithmetic, and multiplication with multi-digit numbers instead of what the school were given. The students were being given multiply a two-digit number by another two-digit number, or that sort of thing, or add up a few three-digit numbers. So I got to working with 4- and 5-digit numbers. I just got pleasure in carrying those out, getting the correct procedure. But the fact that I was motivated to do that, could do that, and always was a sign, of course. And then I had other signs. I had the book E.T. Bell, The Men of Mathematics, at an early age. You could read that. I guess Abel is in that book.
In 1948, when you were 20 years of age, you were admitted as a graduate student in mathematics at Princeton University, an elite institution that handpicked their students. How did you like the atmosphere at Princeton? Was it very competitive?
It was stimulating, and of course it was competitive also. There was a quiet competition of graduate students. They weren't competing directly with each other like tennis players or something, but they were all in the possibility of some special appreciation. Nobody said anything about that, but it was the sort of thing you could imagine.
You were early on interested in game theory, and in fact you invented an ingenious game of topological nature that was widely played in the common room at Fine Hall at Princeton by both faculty and students, and it was called in Princeton Nash, but today it's commonly known as Hex. And there was a Danish inventor and designer, Piet Hein, that independently had discovered this game. How come you were interested in games and game theory?
Well, I studied a little economics in where I was previously in Pittsburgh, Carnegie Institute of Technology, and I observed people who were studying the linkage between games and mathematical programming at Princeton. And I had some ideas, some related to economics and some related to games, like the play of speculators on the stock markets, which is really a game. And I can't put it down exactly, but it turned out that Von Neumann and Morgenstern were both there. They had a relatively, they had a way to the proof of these solutions for two-person games, but that came a simple thing as a special case of the general theorem for equilibrium of n-person games, which is what I found and I associate with the natural idea of equilibrium and with the topological idea of the Brouwer fixed point theorem, which is good material. Exactly when and why I thought of that as something other than what Von Neumann and Morgenstern thought of, I don't know. And then later on, I found out about the Kakutani fixed point theorem, generalization. And I didn't realize that Von Neumann had inspired that he had influenced Kakutani, and Kakutani was a student in Princeton. Okay. So Von Neumann wasn't surprised with the idea of a topological argument for the equilibrium games. But I developed a theory and studied a few other aspects of games at this time.
Yeah, you are a little ahead of me now, because as everyone knows, or well, at least a lot of people knows outside the math community, they are aware that you won the Nobel Memorial Prize in Economic Sciences in 1994. And of course, the film A Beautiful Mind, which Russell Crowe played you in that film. So this became known for a very wide audience. But maybe not everyone knows that the Abel Prize idea was in your thesis that you submitted in Princeton in 1950 when you were only 21 years old. And I guess the name of the thesis was Non-Cooperative Games. Did you have any idea how revolutionary this was going to be? That is going to have impact not only in economics, but fields as diverse as political science and evolutionary biology?
It's hard to say. It is clear that it can be used whenever there is some sort of equilibrium and there are competing or interacting parties. The idea of evolution is naturally parallel to some real situation. I'm getting off the scientific track here.
Yeah. But you realized it was a good work. It was really a good thesis.
Yes, of course. Yes, I had a longer version of it that was reduced a little by my thesis advisor. I had material about cooperative games, but I published that separately.
Okay. When you did write this work, was it on your own, or did you have any help from your thesis advisor, or did you find a topic yourself?
Oh, well, I had more or less found the topic myself, and then the thesis advisor became selected by the nature of my topic.
Was that Tucker? That was your thesis advisor?
Tucker.
Yeah. Mm-hmm. We would like to ask you about your study and work habits. You rarely attended lectures at Princeton. Why?
Well, it's true that the Princeton was quite liberal really was part of the thing. They had introduced, not long before I arrived there, the concept of an N grade, the capital letter N. Like the professor having a course would give a standard grade of N, which means no grade. But this changed, this naturally changed the style of working. I think at that time, Harvard was not operating on that basis, and I don't know if they've operated like that since, but Princeton has continued to be somewhat on the N grade. So the number of people actually taking courses, formally taking courses where grades would be given, is less in Princeton than it might be in some other schools.
Yeah, I heard, I think you have said it yourself, that you took the attitude that learning too much secondhand would stifle creativity and originality. Do you subscribe to that?
Well, it seems to make sense, but one has to say, what is secondhand?
Yeah.
I mean, yes. Secondhand is like you learn not from Abel, but from someone who has been a student of abelian integrals.
While at Princeton, you contacted Albert Einstein and von Neumann on separate occasions. They were, of course, at the Institute for Advanced Study, which is close to the campus, Princeton campus. That's very audacious for a young student to contact such famous people.
Well, it could be done. I mean, that fit into the idea of intellectual functions. Like von Neumann, I had achieved by proof of the equilibrium theorem for game theory using the Brouwer fixed point theorem. And von Neumann and Morrison had used other things in the book. But what happened when I got to von Neumann and I was at the blackboard, he seemed to indicate that he said, and did you use a fixed point theorem for this? Yeah. And I said, yes, I used the Brouwer fixed point theorem. And then I ultimately realized that, see, there was the version of proof using the Kakutani, which is convenient in the economic fixed point theorem, because the mapping is not required to be quite continuous. It has certain continuity properties, generalized properties, and there is a fixed point theorem applicable. But I didn't realize that Kakutani proved that after being stipulated by von Neumann, who was using a fixed point theorem approach to an economic problem with interacting, expanding economy.
I see.
But it was not using it to game theory.
What was von Neumann's reaction to your talking with him?
Well, I was mentioning that I was in his office, and then he just mentioned his sort of, I can imagine now what he knew, that he knew I was not mentioning the Kakutani fixed point theorem. I could have. And I was surprised. He said, yeah. And then I said, yes, of course, this is what I'm doing. And then he said, well, of course this works. And he didn't say too much about how wonderful it was.
But when you met Einstein, talked with Einstein, how did you had some ideas in physics? How did Einstein react?
Yes, well, he had a student there with him, one of his student assistants at the institute. I wasn't quite expecting that, but I went in there, so I was with the two of them, and then I talked about my idea, which related to photons losing energy on a long travel in the universe. And then as a result, will maybe be getting a redshift. Now, other people have had this idea. I saw much later than when I had talked about it then, that someone in Germany wrote a paper about it. Can't give a direct reference.
Okay.
No. But this would also, if this phenomenon existed, then the popular opinion at that time of the expanding universe would be undermined, because there would be the effect that would appear like the effect of the expansion of the universe, sort of a Doppler redshift, could not be validly interpreted in that way, because it could be a redshift of another origin. So there are different ideas which are popular here. I actually talked about ideas. I developed some mathematical theory later on relating to functions, and this developed also to what I'm going to present here as a possibility, an interesting equation, because it's some sort of equation that could describe a different type of space-time. There are some singularities nowadays, since there's different ideas about dark matter and dark energy. So the people who are really promoting it are promoting it that most of the weight, the massiveness of the universe derives from dark energy. But maybe there is none. There could be some alternative theories or some.
I want to move on to John Milnor, who entered Princeton as a freshman when you became graduate students. He was awarded the Abel Prize in 2011, by the way. He said that he made the observation at Princeton that you were very much aware of unsolved problems, often cross-examining people about these. So were you for lookout for famous open problems while at Princeton?
Well, I've been in general aware that Milnor may have noticed something at that time, that perhaps I would look for problems to study, and so on. And he did various things we considered good or spectacular. Well, the seventh sphere is the original thing. Something else was like a great student, but he proves something about any knot in space has at least a certain amount of curvature, but this wasn't really a theorem new by him, strictly accounting, because someone else who is less famous had proved that.
So while you wrote your thesis on game theoretic questions at Princeton University, you were already working on problems of a very different nature, of a more geometric flavor. And you continued this work while being on the staff at MIT in Boston, where you were for a range of years, I believe 1951 to 1959. So in fact, these results that you obtained in this period are the ones that are the main motivation for giving you the Abel Prize this year. And maybe before we get into the precise results that you proved in this period, I would like to give some perspective by citing Mikhail Gromov, who got the Abel Prize in 2009. He told us at a similar occasion that your methods showed incredible originality. And then a little bit later on, I cite, what Nash has done in geometry is, from my point of view, Gromov's point of view, incomparably greater than what he has done in economics by many orders of magnitude. Do you agree?
It's simply a question of taste, I say, but it was quite a struggle, and there was something I did in algebraic geometry as well as differential geometry. It has some subtleties in it, right? Had a breakthrough there, and then one could actually get into controlling the shape, the geometric shape of an algebraic variety.
Right. So that would be my next question. You had a paper on real algebraic manifolds submitted when you just started at Princeton. I think it's October 1951. And I have a citation also here which comes from Michael Artin from the MIT, who later made use of your result. He commented, "Just to conceive the theorem was remarkable." Could you tell us a little about what you dealt with and what you proved in that paper and how you got started to work on this topic?
I thought of it, I was really influenced by space-time and Einstein, the idea of stars distributing around, and I sort of got myself a question. Suppose some pattern of the distribution of stars could be selected. Could it be that there would be a manifold, something curving around and coming in on itself, that would be in some equilibrium position with the distribution of stars? This was the idea I thought about. Ultimately, I developed some mathematical ideas so that the distribution of points, influencing points, could be chosen, and then there would be some manifold that would go around in a desired geometrical and topological way. So I did that and developed some additional general theory for doing that at the same time, and that became published. And then later on, people began working on making the representation more precise, because I think what I proved may have allowed some geometrical, less unbeautiful things in the manifold that's represented. It might come close to other things as well somehow, and it might not be strictly finite. There might be some part of it lying out in infinity. So ultimately, someone else named Wallace claimed to fix that, but he didn't. But he had a fault. But later it was fixed by a mathematician in Italy.
Now I would like to ask you about a second range of results that deals with realizing Riemmanian manifolds. So Riemannian manifolds, loosely speaking, are abstract, smooth structures on which distances and angles are only locally defined in a quite abstract manner. And you show then that these abstract creatures could be realized very concretely as submanifolds in sufficiently high-dimensional Euclidean spaces.
Yes. So if the metric was given some way by through abstract, that what's considered as sufficient to define a metric structure,
yes,
then that could also be achieved by an embedding, the metric induced by embedding. Exactly. And there I got on a sidetrack and first proved that for manifolds with a low level of smoothness,
C1.
the C1, and some other people have followed up on that. But I published something on that, and a Dutch mathematician managed to reduce its dimensions by one.
Nicholas Kuiper, I believe, is that right?
Nicholas Kuiper, yes.
Yeah. So apart from the results, many people have told us that the methods you applied were ingenious. So let me cite just Gromov and Conway. Gromov said that when he first read about your results, He said, I thought it was nonsense, it couldn't be true. But it was true, it was incredible. And then later on, he has completely changed the perspective on partial differential equations. And the famous Princeton mathematician Conway said, what you did was one of the most important pieces of mathematical analysis within the 20th century. So that's quite something. Is it true, as rumors have it, that you started to work on the embedding problem as a result of a bed?
There was something like a bed. There was a discussion in the common room, which is a meeting place for faculty at MIT. And one of the senior faculty, he did work in geometry. I discussed with him the idea of embedding, and I realized then I got from him the idea that at that time, the embedding area, the realization of metrics of embedded thing was completely open. There was nothing there. And that was Professor Ambrose, or Nirenberg. And then, so I decided to work on, I began to work on it, but then I got shifted into C1. And it turned out that one could do it in C1 dimensions with very little excess of dimensions. Dimensions of the manifold over the space embedded could be 1 or 2. Mm-hmm. I did it with 2, but then Creeper did it with only 1. But this didn't do it smoothly, which seemed the right thing. Yes. You're given something smooth, you have a smooth answer to what you're doing. But in a few years, I got the generalization to smooth. But I published in a paper with 4 parts.
And this continued then with your work on PDEs proper, if I may say so. So I think it came out of a conversation with Louis Nirenberg, the Abel Prize recipient that you are sharing the prize with at the Courant Institute in New York. And we understand that he told you about a major unsolved problem within nonlinear PDEs.
He told me about the work of De Giorgi. And there was something that had been done by a professor in California in 2 dimensions. But the work had not been extended past 2 dimensions. The question was possible. There was some problem in the continuity property of a solution of a partial differential equation was found to be intrinsic in 2 dimensions by this California, what's his name, I forget his name. He's died some time ago. But that's what I got to work on, and De Giorgi got to work on it also.
But you didn't know of each other's work at the time?
No, I didn't know of De Giorgi and his work, but he did solve it first.
Yes, in the elliptic case.
Yes, well, it was really the elliptic case originally, but I sort of generalized to include parabolic equations, which was very favorable. So with parabolic equations, the method of getting an argument relating to an entropy concept came up. And I don't know, I'm not trying to argue about precedent, but a similar entropy method was used by Professor Hamilton in New York, and then by Perelman.
Yes.
They used an entropy which they could control in order to control the improvements that they were making in this. So
that's what led finally to the proof of the Poincare conjecture, right?
Well, they used the entropy as quite essential.
Yes. Mm-hmm.
And of course, Hamilton used it first And then Perelman takes it up from there, calls it on far to the recognized success.
Coming back to the time when De Giorgi and you worked more or less on the same topic, when you first found out that De Giorgi had solved at least part of the problem before you, were you very disappointed?
Well, of course, it's disappointing, but one tends to find some other route, like water is built up in the lake that might but the outflow stream is blocked in one place, so it may come out another way.
Yeah. Some people have been speculating that you might have received the Fields Medal if there hadn't been the coincidence with the work of De Giorgi. Have you?
Well, yes, that seems a natural thing, and De Giorgi did not get the Fields Medal either, though. He did get some other recognitions. Yes, but
So
these are this is not mathematics. Thinking about how some sort of selecting body may function. It's better to be thought about by people who are sure they're not in the category of possibilities of targets.
So let's move forward to a turning point in your life. We've been told that you decided to attack the arguably most famous of all open problems in mathematics, the Riemann Hypothesis, which is still wide open and is one of the Millennium Prizes that we talked about on the list of the Clay Foundation. Could you tell us how you experienced mental exhaustion as a result of your endeavor?
Well, the thing is, I think this is sort of like a rumor or a myth that I did actually make a frontal attack on this. I have some cautiousness, and that way I'm a little cautious about my efforts where I try to attack some problem, because the problems can attack back. So I don't think of myself as an actual student, maybe a casual, whatever I could see. It's very beautiful and interesting what you could see about it. If there's anything new. Now, some people near me did some. Professor Salberg, who's a Norwegian mathematician, he's about the time of World War II, I think, the first part of it. He proved that there was at least some finite measure of these zeros that were actually on the line. And though they become a different type of zero, it's like a double zero that appears as a single zero. And he proved that it was a very small fraction, but that was proved at an early time before he was at the Institute. He did some good work at that time. And then later on, a professor where I was in MIT, he proved that there was a good fraction, like around the quantity of 1/3 of the zeros of the Riemann function were actually on the line.
That was Levinson that did that?
And then at that time he seemed to have been suffering from brain cancer, which he died from. That's how things can happen. Your brain can be under attack, and yet you could do some good reasoning functioning for a while.
Mathematicians in your surroundings describe that your attitude to working on mathematical problems is very different from what most other people do. Can you tell us a little bit about this different approach and what is the source of inspiration for you?
Well, I can't argue as if at the present time I'm working in such and such a way which is different from another more standard work, another way. I try to think of what can I do, what is with my mind and my experiences and connections, what is might it be favorable to me to try. So I don't think of trying anything or just the latest popular announcement.
What about, it's known that when you were in Princeton, you were biking around campus whistling Bach's Little Fugue. Are you like classical music?
Yes, I do like Bach.
Other favorite composers than Bach?
Well, there are a lot of classical composers that can be quite pleasing, and you hear a good piece, like Mozart. They're so much better than other composers. That's the thing. Pachelbel.
Could I interject one question that I think you have said in an interview, you may correct me, something like, I wouldn't have had good scientific ideas if I had thought more normally.
If I had
thought more normally, you were sort of out of the main, that's something that you had a different way of looking at things.
Well, it's easy to think that, and I think that is true for me, just as a mathematician. Yes, it wouldn't be good to just think like a good student doing a thesis. Most mathematics theses look pretty routine. There's a lot of work that's sort of set up by the thesis advisor and increased till it's heaped up enough, and then the thesis is recognized.
Okay, I think we have to come to an end. So we would like to thank you very much for a very interesting interview. And this is, apart from the two of us, it's on behalf of the Danish, the Norwegian, and the European mathematical societies that we represent. Thank you very much.
Thank you.